Hi, hello, and welcome. This is Greg Jacobs from Woodbury Forest School in Central Virginia. I teach at a boys' boarding school, and all the students are gone right now. I'm really glad to be with you today. We're going to be talking about AP Physics 1. Now, I know that you are probably well aware, but just in case, the AP Physics exams will go on. They will be administered online at home somehow in some dates. We don't know. We will find out details on April 3rd. Until then, we just have to focus on learning physics. It doesn't matter what the format of the exam is, as long as we can do good physics, you're going to do great. If you can't do physics, you're going to have trouble, but that's okay. You can work with me these next few weeks, and we will figure out how to do some good physics. Know that there are no circuits, electricity, or waves on this year's exam. So we're going to focus on forces in motion, energy, and momentum. And today we're going to talk about motion in terms of rotational kinematics. So let's go over to here. This is what we're going to talk about today. I want to start with an idea about culture building. See, I'm not going to give you one weird trick that you can use that will allow you to game the test. That's not how you learn physics. Instead, I'm going to help you understand physics from the ground up. And I challenge us to have a culture of students that are all learning AP Physics 1. Find somebody who is a little bit better than you at physics and ask them to help you, not to do your homework for you, but to help you understand the concepts in the way that they do. Then I challenge you to find somebody who's not quite as good at physics as you are and help them understand. Don't do their homework, just help them understand what they're doing. And that will lead to a beautiful culture where we're all increasing our understanding. If you would like, during today's lesson, you can go to Jacobs Physics on Twitter, and we can start that community. Feel free to ask questions, make comments, meet some other people. And toward the end of the lesson, if I have time, I'll try to improv based on some of the things that are coming across there. So right now, we're going to start with not rotational kinematics. We're going to start with linear kinematics. Why? Because rotational kinematics calls back to what you probably learned early in the course. Let me show you. I got a projectile launcher here. Boom. The projectile launcher shoots a ball upward at about 4.8 meters per second. How do I know that? I tested it a million times over the course of my career. And our prediction is going to be, how high does this go? You can't see that because it goes higher than your screen page, but I want to know how high that is. This is a straightforward kinematics problem. How do I suggest you solve those problems? I suggest you use a table of the 5 major kinematics variables: initial and final speed, displacement, acceleration, and time. We start by determining a positive direction. I'm going to roll a die. 1 through 5 means positive is up. All right, positive is up. And then we're going to say, what part of the motion are we considering? We're going to consider from the launch to the peak. That is, the initial velocity is not 0 because we're not considering from before the launch. The initial velocity is 4.8 meters per second. Which way? Upward, so positive. The final velocity is at the peak. Well, at the peak, the ball stops moving for just a moment, so the final velocity is 0. The displacement is what I asked you to figure out. The acceleration, this ball is in free fall. So in free fall, we know that all objects have an acceleration of 10 meters per second, and that acceleration is, gravity still acts down, so negative. What's the time frame that takes? Well, I know that a lot of you who are trying to work this problem with me are going to say, well, don't you just divide this number by this number? No. If you don't know, if the problem does not state exactly what a variable is, you just put a question mark, and that's fine. Why is that fine? Because a kinematics problem is solvable if we know 3 of the 5 variables. 1, 2, 3. We know 3 of the 5 variables, therefore, the physics is done. The rest is just mathematics. Now, a lot of you are saying, well, the mathematics is the hard part, but there are a vanishingly small number of AP problems that are going to ask for a numerical response. I'm going to do this numerical response problem here because I want a prediction for how high that ball goes. We're going to use the constant acceleration kinematics equations. And I'm going to use that one because it seems to work. I just rewrote it again. I don't know why I did that, but I'm going to plug in my zeros and I'm going to solve for what I'm looking for. Now I'm going to plug in what I know. And I'm going to solve this out. 1.2 meters, 2 digits. So what that really means is that when I launch this ball, it should go 1.2 meters above the launch point. The AP exam is less likely to ask you for this number as they are to say, well, how would I measure that height? How would I do an experiment to figure that out? Well, I'm going to launch this. I'm going to put a meter stick in the background, and we know that this thing should go about this far above the meter stick. Now, I can't do that for you live, but if we go over to this other camera, I did this the other day. This is a program called Coach's Eye. You can also get Huddle Technique. And if you look closely, you can see when I advance the video, there is the ball. And there's the peak of the ball's flight. What this video can do also is, look at this, this is cool. Whoop, right there is where the ball launches, right? I'm going to put a timer on there. When the ball reaches the peak of its flight, that's 0.49 seconds. You can go back and solve the equations we were just dealing with for time, and you'll probably get something pretty darn close to that. Isn't that cool? All right, so that is the background, but let's talk about what you need to know for rotational kinematics, because that's what I was supposed to be talking about. Rotational kinematics talks about the motion of this disk here. You see this little black spot? Watch that black spot go around. And we're going to be talking about not a ball moving in a straight line, but this disk rotating. So what are the 5 important kinematic variables for rotational motion? Well, they are angular velocity. How fast is this spinning? And not linear displacement, but angular displacement. How far around does this disk go? Let's talk about angular displacement. That's an angle which is measured in degrees, right? Well, we don't want to measure in degrees, we want to measure in radians. So let me ask you this question. What's a radian? I know a lot of you are saying something that involves the unit circle or 2 pi, but a lot of you aren't really sure. Let me just give you an answer of what a radian is. It's a slice of pi, P-I-E, pi. It's about 1/6 of a circle. There are 6 radians in a circle. So when this dot goes around 1 full time, like that, that should be about 6 radians. Don't believe me? That thing there is a rotational motion probe. Hopefully you can see this right now. There, it focused. I'm connected via Bluetooth to that rotational motion probe, and I'm going to measure an angle in radians. I'm going to start, and when I move, it moves. I'm going to 0 up at the top here. Whoop. So now I'm going to move this exactly 1 rotation. There it is, about 6 radians. Don't worry about the 6 in a bit. It's just about 6 radians. All right, so now let's stop that and go back to the video. Now what I'm going to do is a kinematics problem. I'm going to start this thing here and watch, this dot's going to go around about 2 times. So that's 12 radians. And I want to know what will be the rotational speed of this disk when it's gone around 12 radians, 2 rotations. I'm also going to tell you that the change in speed every second is 18 radians per second per second. This speed changes 18 radians per second every second. How do I know that? Well, I measured it beforehand with my little device. Knowing that information, I want to know what will be the angular velocity right now. How are we going to solve that? Well, we use rotational kinematics. Rotational kinematics works the same way as linear kinematics works. Instead of initial and final linear speed, displacement, and acceleration, we use initial and final angular velocity. angular acceleration, and angular displacement. The three basic kinematics equations are identical, just with omegas, that's a Greek omega representing angular velocity, and alphas representing angular acceleration, and thetas representing angular displacement. So let's do the problem. There are my 5 basic kinematics variables. We started from rest, so the initial angular speed was 0. We're looking for the final angular speed. The angular displacement was 12 radians because it went around 2 times. The angular acceleration, I told you because I measured it earlier, is 18 radians per second per second. I don't know how much time that took. And then I'm going to solve using those kinematics equations. You're specifically going to use that one to start with. And I did the math earlier, and it's going to give you 20 radians per second as a little bit under that, like 19 point something radians per second at the end. So let's do this. Once again, here's the live version. I couldn't figure out how to split the screen here, thanks to Claire and all of the people at College Board who were trying to get this split screen. You're going to see that, and I'm going to press play and make a velocity time graph for you. So if we go back here, we're going to do angular velocity versus time. Let's get rid of that one. And let's spread that out, spread that down. Come on. There we go. We're expecting that the maximum angular speed will be just under that. So are we ready? Look at that, just under 20 radians per second. Physics works. Isn't that amazing? I hope you can see that. I'm seeing that my screen's a little out of focus, but there it is. 20 radians per second, just under. We like it. All right. That's not the point of AP Physics. I told you there will be a vanishingly small number of problems on the AP exam that simply ask you to plug numbers into an equation. Okay, Greg, so what is going to be there? Well, let's ask a question based on semi-quantitative reasoning. All right, we already figured out what happens in that case. Let's cut the angular acceleration in half. Now the angular acceleration is half of what it was before. That's going to be 9 radians per second per second. Now, what will the final velocity be, the angular velocity at the bottom? How many times bigger or smaller will that angular velocity be? Does the angular velocity double, triple, quadruple, cut in half, cut in less than half, more than half? Anybody who already has an answer is doing this problem wrong. Even a physicist doesn't know the answer. That's not how physicists work. Physicists know the correct approach to take, but they don't know the answers to these questions. That's like knowing before you even do any calculation that the answer is 20 radians per second. That's not what we do. What we're going to do is we're going to try the factor of change method. Let me show you that. To use the factor of change method, we start by solving in variables for what we're looking for. We're looking for the final angular velocity. So we're going to use this equation. We are going to plug in our zeros, solve for what we're looking for. Now, instead of plugging in numbers, I mean, you could plug in numbers and get the answer and then compare that to the original, but instead of plugging in numbers, we can do this right away very quickly. Plug in 1 for anything that doesn't change and plug in the factor of change for what does. So let's see here. The final angular velocity is the square root of, how does the number 2 change? It doesn't. It doesn't, so put in a 1. How does the angular acceleration change? We said that we cut the angular acceleration in half, so plug in a half. How does the angular displacement change? Well, we're still causing that disk to rotate twice. That's 2 rotations, that's 12 radians, that's the same displacement that we had before. So the angular speed changes by a factor of the square root of 1/2. So if you plug in the square root of 1/2, 1 over the square root of 2, you get 0.7. The new angular speed will not be half of the old angular speed, but will be somewhere in the neighborhood of 70% of the old angular speed. Do you believe? You shouldn't. You should make me do the experiment. And I'm going to do the experiment. I'm going to do this. So you can see it live. Now you can see what this does. Are we ready? There we go. We didn't cut the angular speed in half. We cut the angular speed by something else, 14 radians per second at the most. So that's about 70% of the original 20 radians per second. Isn't it amazing when physics works? I love it. All right. Let's continue along. I got another cute little slide here. Let's talk about graphs. Hope you can see that. When we're dealing with velocity time or position time graphs, there are basically 3 or 4 facts to know. Screenshot this, make this part of your studying for the AP exam. I suggest that anytime you have a graphs question, you start that graphs question with one of these facts, not with the answer, but with one of these facts. So if we're asked, what is the angular acceleration here? How would you determine that from the velocity time graph? Well, we say to determine the object's acceleration, we take the slope of the velocity time graph. So in the second case, we can take the slope of the velocity time graph. Turns out it was 8 radians per second, pretty darn close to the 9 radians per second I suggested it was. All right. How did I know that that thing moved 14 radians per second at the end? To determine how fast the object is moving, look at the vertical axis of the velocity time graph. I just read the vertical axis each time to get the angular speed. So let me do one quick problem here. What would a velocity time graph look like if instead of starting this thing up here and releasing it, if instead I did this? Just describe kind of what that velocity time graph would look like, where the dot slows down and then speeds up in the other direction. Well, we know that the angular speed is determined by the vertical axis. The vertical axis values have to get closer to 0 and then farther from 0 because this thing slows down and then speeds up. We know that to determine which way the object is moving, that's one of the facts from the sheet that I just showed. To determine which way the object is moving, look at whether the velocity time graph is above or below the horizontal axis. So this graph should start either above or below the horizontal axis and end up on the other side of the horizontal axis. Let's take a look. Is it showing? Nope, let's go back here. So I'm live here. Let's try again on the document camera. There we go. Okay. I'm going to get rid of those. I'm going to start this. Look at that. The graph started below the horizontal axis. The vertical axis values got closer to 0. And then the angular velocity ended up above the horizontal axis with the vertical axis values getting farther from 0. Don't worry about the negative signs. A negative sign just indicates the direction of motion on a velocity time graph. I understand that in calculus, you would say that this function increases. That doesn't mean the speed increases. The vertical axis values get closer to 0. You can't speed up and end at 0 speed. More to the point, it doesn't work if you're pulled over for speeding and the officer says you were going faster than the speed limit. You can't say, no, I was going south. South is the negative direction. So my speed, my velocity, excuse me, of negative 100 meters per second is clearly less than the posted speed limit of plus 65 miles per hour. You can't do that. It's not going to work. So don't worry about negative signs. They don't mean much. Position time graph facts. The big one here is to determine, well, there's 2 of them, to determine which way an object is moving. Look at which way the position time graph is sloped. That is a front slash or a back slash. And to determine how fast the object is moving, look at the steepness of the position time graph. I'm going to turn this velocity time graph into a position time graph. Let's think about what it might look like. We know that when the speed is 0, we know that the slope of the graph, the steepness of the graph, must be 0. That means the graph has to be a horizontal line at that point when we switch to position time. And when the graph shows slowing down, that means the steepness of the position time graph must get shallower. And when the object speeds up, the graph gets steeper. Let's look. Look at that. The steepness gets shallower until the graph is not steep at all when these objects stop briefly, because the slope of the graph is the speed. And then the steepness gets bigger again until we're done. That's a position time graph, an angular position versus time graph. All right, good stuff. Let's do a bit of a problem. This is not exactly an AP question, but it's one that could be an AP question. Give you a moment to read. I hope like heck you can read this. I'm going to read it to you just in case. This disk is spinning about an axis that passes through the center of the disk. And we want to know, in experiment 1, this is the velocity versus time graph, the angular velocity versus time graph. And now in experiment 2, we change the initial angular velocity of the disk. We double that initial angular velocity without changing the angular acceleration. So the first question is, sketch the angular velocity as a function of time for experiment 2, where we double the initial angular speed. So let's use our graph facts. On a velocity time graph, the vertical axis gives the initial speed. So if we're going to double the initial speed, then we need to double the vertical axis value at first. So that's where we should start. On a position time, or on a velocity time graph, the slope of the velocity time graph determines the acceleration. Notice that I'm not really caring whether I speak in terms of angular or linear quantities. It's the same fact. On an angular velocity versus time graph, the slope indicates the angular acceleration. So we want the same slope. That should look about like that. There we go, something like that. Part 2 asks, explain the features of your sketch, including the horizontal and vertical intercepts. When you're asked to explain, that means use subjects and verbs. In all cases, an explanation, a justification, anything that's beyond a calculation or a derivation needs subjects and verbs. A paragraph response needs about 5 sentences with subjects and verbs. Just an explanation, just a couple sentences with subjects and verbs. So how would I describe, how would I explain the features of my sketch? I would use those facts. I would say, the vertical axis of a velocity time graph indicates the speed. The speed initially was doubled, so the vertical axis value at the beginning must be doubled. Then I would say the angular acceleration is the slope of the velocity time graph. Since we kept the same acceleration, we should have the same slope, and therefore the horizontal intercept should double, as you can see in my sketch. That's what I do. All right. Moving on. Lesson overview. I want to oh, that's what I want up there right now. And one more time. There we go. These are the things I had planned, and I have gone through predicting the maximum height of a launched ball. What is a radian? Predictions based on the quantitative demonstrations. We've talked about position time and velocity time graphs, and we've done a little semi-quantitative reasoning with an AP problem. So let me check real quick. I see that there are bobzillion notifications here. Yeah, I don't know anything about the lag here. I am just talking and doing my best in my classroom. And hey, looks like some people are seeing everything is fine here. And let me take one or two more questions here. Somebody says, just remember that you shouldn't be measuring in degrees if you want to have a rad time. Very nice. I'll point out, if you do measure in degrees and describe motion in terms of degrees, if you had told me, hey, this thing is going to go around twice, so that's going to go around 720 degrees, nobody's going to complain as long as you're very clear with your units. Now, your mathematics, if you're asked for a numerical answer in radians per second, aren't going to work. But you notice that you don't have to say a word about radians if you wanted to do that semi-quantitative reasoning question, where we just showed the factor of change. I can't find it over here. Where we showed the factor of change. You don't need any numerical values, so it doesn't matter whether you measured in radians or degrees. If you're more comfortable talking in degrees, go for it. But if you just think of a radian as a sixth of a circle, then suddenly it doesn't matter whether you're, it's not hard to think in degrees. Will the three kinematics equations be provided for us, or will we need to memorize them? That's a great question. They will be provided for you, absolutely. But, and there's nothing wrong with double checking and searching back and say, hey, is it delta x equals v naught t plus 1/2 at squared or 1/2 at? That's fine. I do think you should have those in your brain. You shouldn't be going hunting and pecking on the equation sheet. If you're saying, ooh, the question asks for an angular displacement, I need to go find an equation with a theta in it. That's not a great approach to AP physics, because you might find an equation like v equals r theta or something that doesn't even apply to that situation. And especially if you take physics 2 and you get n1 sine theta 1 equals n2 sine theta 2, that's not what we're looking for. So I'd be very careful about hunting and pecking. Know these equations, have them in the back of your head. But if you need to know a detail, they're there for you, I promise. What else do we have here? Oh, hello, I see for the acceleration A, use the value -10 meters per second per second. In my class, we also use -9.8 meters per second. Does the College Board care which value we use? Great question. What's the difference? No, I mean mathematically, what's the difference? The difference is 2%. And when we're dealing with predictions in lab, I couldn't tell you more than 2% how high this thing went. 2% would be like 2 centimeters here, and I couldn't tell you whether that thing went 120 plus or minus 2 centimeters. I can tell you it went 120 plus or minus 10 centimeters. It doesn't make any difference. Use 10 meters per second, because to me, 10 meters per second means the object changes its speed by 10 meters per second every second when something is in free fall. 9.8 meters per second squared, that's a mean. Notice that I don't say meters per second squared. I don't say radians per second squared. Tell me, what's a second squared? You don't know. Angular acceleration is the change in angular speed every second. So we say the speed changes by 18 radians per second every second. The speed of this ball changes by 10 meters per second every second. What about the negative sign? If you recall, when I did the problem, I flipped a coin to see whether up would be positive or down would be positive. It doesn't matter. I rolled this die. If this die had come up 6, then I would have used negative signs for up, and I would have used positive signs for down. It doesn't matter which direction you choose as positive. The negative and the positive sign just mean which direction something is moving. And then when something is speeding up, its acceleration has the same sign, is in the same direction as the velocity. When something slows down, the acceleration is the opposite direction of the velocity. On this problem that I did, come on, DocCam. I have to switch back and forth twice sometimes to get this. There we go. Notice that the ball was slowing down in my initial demo. So the positive and the negative signs on velocity and acceleration are opposite, which means the ball was slowing down, which it was. I have 15 more minutes max, so I will talk again. Kevin Q asks, will the review course cover units 1 to 7? Yes, we will cover eventually everything that involves something that is on the exam. That is mechanics only. No waves, no circuits, no electricity. That means we are talking about forces in motion, conservation of energy, and conservation of momentum. Every mechanics problem can be approached in one of those three ways. And tomorrow, you're going to be working with Josh Beck of North Carolina. He's awesome. He is going to be doing some live demonstrations from his house on torque and equilibrium. I'm going to give you an exam question that you can play with so that that will lead into his lesson. You'll have a good time with him. He's awesome. What else do you want to show me? I have 20 more notifications plus. It says linear kinematics is not often tested in isolation. Do I feel the same is true for rotational kinematics? Yes, I feel that way about everything. On a free response problem, you'll see that it usually has at least parts A and B, if not A, B, C, D, E, and F. And I consider the units that I teach between now and the exam itself as a, quote, putting it all together unit. We've already studied all these topics in isolation. Now is the time to put everything together. I don't think Newton's laws are tested in isolation ever. I think that on a free response problem, you have to be able to do a rotational kinematics problem and then talk about, okay, well, now go back and do the two-body problem to figure out what's the tension in this rope. Not going to do that today, but we will have a review session on two-body problems, make two free body diagrams. Yeah, we'll deal with that. We'll also have a number of review sessions. We also will have a number of review sessions that focus on old AP questions from the last 5 years or so, because that's how long AP Physics 1 has been in existence. Going back to the questions here, will I provide the papers that I used in the video today for us to study with? You're going to have to go back and freeze frame on those. I guess I could take some pictures of these. I guess if you really want a souvenir of today's lessons, first person to find my email and email me and request these with a home address. You probably shouldn't do that. I'm going to say I should give these away as a special prize. I don't know. Go back and just freeze frame on those, because you can pause the video here. This will be recorded for you to look at later. That said, a lot of people, when I do these kinds of quantitative demonstrations, write feverishly trying to do the math. Yeah, it is a good exercise to go back and see how those mathematical relationships work. To, for example, try to predict how much time it took for this ball to reach the top, to try to predict how much time it took for this thing to come to the ground. That's a great exercise, and you can check your answers with the video that I showed and with the velocity time and position time graphs that I showed. That said, don't worry about the mathematics so much. Worry about, do you understand the principles? Do you understand the factor of change method that I showed you? Go back, try the factor of change method on one of the problems from your class that you've been doing this year. The problems that I'm going to give you for tomorrow involve position time and velocity time graphs. But there are a million other practice problems that you can get from your teacher via AP Classroom. And these are techniques that I hope you will use in the future. What else we got here? You're kind of lost in the factor of change process. Do you mind explaining it again? I'll go through that one more time. Let me do that with, let me go show you this. This is the original question that I asked, where we have a ball thrown up at a speed of 4.8 meters per second, and we want to know how high does it go? Well, let me go back and ask, well, what happens if the initial speed were doubled? That's a factor of change question, a semi-quantitative reasoning question. All right. We solved the problem the same way we did, except we use variables. We start with Vf squared equals V naught squared plus 2a delta x. Final velocity was 0. We're given acceleration and we're looking for displacement, so we solve for that. And there's our response for the displacement. But what if V naught were doubled? Now we use the factor of change. Factor of change is going to give us plugging in 1 for anything that doesn't change, plugging in 2 for anything that doubles. Initial velocity doubles, and that's squared. The number 2 does not change. That's what's elegant about this. If it doesn't change, we plug in a 1. The acceleration doesn't change. So what does this give us? 2 squared over 1 is 4. The factor of change is 4. That means if I double the initial speed, this ball is going to go 4 times higher. And we can see that physically. I'm going to use the lower setting here. This is something like 3 meters per second initially. If I doubled that speed, and this is more than double, I can't actually get it. If I doubled that speed to 6 meters per second, the ball wouldn't just go twice as high. It would go 4 times as high and go above the ceiling here. Great question, and I hope you can try factor of change with a few other problems that involve semi-quantitative reasoning. I've given you 2 examples now, but now go out and try this on some of your old homework problems. Go give each other problems, pose each other's problems in the Twitter feed. Go meet somebody on a Twitter feed and go Zoom with them and pose each other factor of change questions. Let's see what else we got here. We have 8 minutes remaining, and I will take one more here. That's already there. Can I go through the graph on the example question? Here's the example question. The graph asked me, sketch the angular velocity as a function of time for experiment 2. Experiment 2 is when we doubled the initial angular velocity of the disk. The angular velocity of the disk is given by the vertical axis value. Since I doubled the initial velocity of the disk, the initial vertical axis value is also doubled. The angular acceleration does not change. Therefore, the slope of this graph does not change. Those are basically the only facts you need to know about angular velocity versus time graphs. I guess there is one more that says the angular displacement is given by the area under the angular velocity versus time graph. So you can show that in the first case, in experiment 1, that's how far the disk rotates. And in the second situation, that's how far the disk rotates, a lot farther. That's the graph. There really isn't much about graphs. If you go back and freeze frame on your velocity time graph facts, and I've got them right here for you again, that's it. If you know these 4 facts of physics, you can do anything related to velocity time graphs. And when you do anything related to velocity time graphs, you should always start with one of these 4 facts. One more question, why not? They're coming fast and furious. What did I have for breakfast? That is an interesting question. I had a large cup of coffee for breakfast. These are crazy times, and we are no longer on any kind of regularly scheduled meal schedule. I'm almost back to what it was like when I was in my second year of teaching, and it was over the summer, and I was preparing classes all day, and I was eating at noon and at midnight. Really strange. My son, who got a 5 on the AP Physics exam a couple years ago, he's still in school online, and we see him once in a while coming down the stairs saying, "I'm hungry," and there's no rhyme or reason to it. It's an interesting time, and what I have for breakfast is pretty much nothing every day, but I'm having good lunches and dinners. Anyway, we are. I am ready to move on to. Oops, that's not it. I got an Alt-N for you. AP exam practice. This is what Josh is going to start tomorrow with. Come on. Let's get it a little bit out there. There we go. I hope that that comes across. If it doesn't, I will screenshot this and send it to people so we can post if necessary. But this is our problem for tomorrow. I'll read it to you. In a new experiment, this is the same setup that we had before, the disk's angular acceleration is reduced to 0. Assume the disk's initial angular velocity is omega d, so sketch angular position versus time and angular acceleration versus time. And then in part 2, we once again double the initial angular velocity, but still with the angular acceleration reduced to 0. Sketch graphs of angular position versus time and angular acceleration versus time. If you have a chance, do these. I'm not going to give you the answers, but I am going to one more time put up the angular velocity versus time facts. And I already put up the position versus time graphs. They're around here somewhere. Use the facts and you'll be able to answer that question. All right, that is all for today. Josh Beck of North Carolina, one of my good friends, he is awesome. I've graded AP exams with him. He will be back tomorrow, noon Eastern time, and he will start by going over that question I just posed, and then he will continue and do experiments with torque in equilibrium. He'll be balancing a meter stick. Then on Friday, I will be back with you. And I will be doing an experimental question, an AP level experimental question. And our focus will be on how to approach an experiment. It will be about torque and equilibrium, but it will really be about how do we measure force? How do we make a graph that is that can be used to determine an unknown variable by using the best fit line? We'll have a good time with that. That will be on Friday, starting at 12 noon Eastern time. And then next week we will publish a schedule, but trust me, every day will be useful to you because even if I'm not covering content that you are unfamiliar with, we will be talking about the skills that are on the AP exam, like factor of change, like making a kinematics table, like measuring and recording how high this ball goes, like using this probe. We'll be using all kinds of skills that will be useful to you when you take your AP exam. So until Friday, this is Greg for Bertha. Say goodnight, Bertha. Or say goodnight, Edna. I'll see you later. Good night.